Swayam Prabha. Digital India. Educated India.
Welcome to Module C, Lecture 2. In this lecture, we shall continue our discussion about analysis of shock waves. What we discussed in our previous lecture is the qualitative approach for analysis of shock waves, and we took two examples: shock waves at signalized intersections and also how the shock waves are generated due to lane drop and at different flow levels. I also mentioned to you about the classification of shock waves, stationary and moving. Stationary again frontal, rear, frontal stationary, rear stationary, and moving shock waves may be again forward, backward, forming or recovery. So, forward forming, forward recovery, backward recovery. With this background, today we shall focus on quantitative analysis of shock waves. As you know, the shock wave is the point that demarcates two stream conditions. Along the length of the road, when we travel, the stream conditions are not same, they vary. So, wherever the stream condition is changing, a boundary is created, and this boundary which demarcates to stream condition is the shock wave. Shock wave is started when two stream conditions they meet. So, let us consider two stream conditions A and B with speed u, density k and flow q. So, for A and B it would QA, UA, K and KB, QB, UB. Now, the demarcation point when the two stream conditions are meeting, the demarcation points may move forward with means in the line of the movement or along the movement of the vehicles, in the direction of the movement of the vehicles, or move backward in the direction opposite to the direction of the movement of vehicles, or stay at the same point with respect to space and time. The rate at which the demarcation point moves is referred to as the speed of shock wave, how that point is moving. The rate at which the point moves is referred to as the speed of shock waves. Now, if we consider two stream conditions A and B as I have mentioned, and they generate a shock wave with a speed of omega a b, as shown here, this is stream conditions A, this is stream conditions B in the time distance diagram, and they are meeting. So, a shock wave is created and the speed of this shock wave is omega a b. Now, if you consider speed of vehicle in flow condition B relative to the speed of shock wave, speed of shock wave, what is that speed? That is u b minus omega a b. u b is the speed of vehicles travelling in traffic state B, and omega a b is the speed of shock wave. So, what is the speed of vehicles in flow condition B relative to shock wave speed? That is u b minus omega a b. Similarly, what is the speed of vehicles in flow condition A relative to the shock wave speed? In traffic state A, vehicles are moving with the speed u a, and the speed of the shock wave is omega a b. So, what is then the relative speed of vehicles in flow condition A? relative to shock wave speed, that is u a minus omega a b. Now, at shock wave boundary, if we consider two stream condition and this is the shock wave boundary, the number of vehicles leaving flow condition B must be equal to the number of vehicles entering in flow condition A. These two numbers must be equal, because shock wave is a boundary. So, the number of vehicles leaving flow condition B, let us call that as NB, number of vehicles, and the number of vehicles entering the flow condition A on the other side, let us call that number as NA. So, this NB and NA cannot be different, they must be same. So, how we can calculate NB? How many number of vehicles are leaving flow condition A? It is the flow QB multiplied by T. What is QB? How we can know flow rate? It is Q equal to U into K, but here relative to shock wave, what is the speed? UB minus omega AB. So, it is UB minus omega AB within bracket multiplied by density, that give me the flow into time t. You can call it t, you can call it delta t to indicate small time interval, we are talking about a small time interval. And similarly, what is NA? NA equal to QA into T, and what is QA? UA minus omega AB, the whole in the bracket multiplied by K, that is speed into density equal to flow multiplied by time t or delta t, whatever you take. Now, this NA and NB must be equal. So, you make them equal, and if you do that, eventually you then find a very interesting thing, that omega AB equal to QA minus QB divided by KA minus KB. What is it? What does it mean? What is the physical interpretation? We are actually connecting 2 points on the flow density curve, connecting 2 points A and B, and the slope of that line is actually QA minus QB divided by KA minus KB. So, slope of the line joining 2 points on the flow density curve, that slope is actually the speed of the shock wave, which will be generated at the meeting point of those two flow conditions A and B. So, that is what I have said. In flow density curve, speed of shock wave is then equal to the slope of the lining joining the points representing two conditions in the flow density curve. Now, given this background, when then a forward moving shock wave will be created? Forward moving means with a positive slope. Obviously, the line slope of this line will be positive only when a stream with lower flow and lower density, lower flow, lower density meets a stream with higher flow, higher density, then only the slope will be positive. That is what you are seeing here. So, always a forward moving shock wave will be created when two stream conditions are meeting, one with low flow, low density and the other with high flow, high density. That is the context where a forward moving shock wave will be created. Similarly, when a stationary shock wave will be created, slope 0, horizontal, That means same flow, but two different densities. So, a stationary shock wave will occur when the streams meeting have the same flow, but different densities. You can see this line. Same flow, then only the slope will be 0, but two different densities. K values are different. Now, what is remaining is the backward moving. You can understand when the slope will be negative, when a stream with higher flow, flow wise higher, lower density, flow wise higher, density wise lower, meets a stream with lower flow and higher density. So, one side the traffic stream is having higher flow, lower density, the other side lower flow, higher density. So, now we know based on the analysis, quantitative analysis, and based on the understanding of the speed of shock wave, we can tell now when the forward moving shock waves are likely to be created, when the backward moving shock waves likely to be created, and when a stationary shock wave is likely to be created. Now, let us try to analyze different types of shock wave based on this quantitative analysis, taking reference first with an signalized intersection. The context is known. Vehicles are arriving during the green time, passing the stop line or the signal without stopping, without slowing down. So, flow condition A exists on both upstream and downstream of the signal or the stop line. Then the signal becomes red and therefore, a new traffic state B is created. Once the traffic state D is created downstream of the signal during the red time, because traffic stream condition in A and B, D, A and D, these two stream conditions are different. Then once the signal turns from red to green, again the vehicle get discharged with a traffic state, flow state C, and then multiple shock waves will be created because of this whole phenomena. Why we are interested in shock wave analysis at signalized intersections? For various reasons. Shock wave analysis at signalized intersection may be necessary because of the length of the queue interfering the upstream traffic. This is one possible reason. There are many other purposes the analysis may serve. Say the queue length is really important, because queue from the right lane might be blocking the through traffic. The right lane storage lane is exhausted and the spillover of vehicle is there, which are actually right turning vehicle, and that is altogether moving the through movement. Through vehicles are not able to pass because the right turning vehicles are waiting in front of it, in front of those vehicles. Or queue is extending upstream to block the intersection, that might be happening. So, we must do analysis what is really happening when this traffic state B, how much it is forming, to what extent the formation is happening, when the traffic state is really getting dissipated, whether it is getting dissipated within a reasonable time, what is the maximum queue length, how much time it is taking to dissipate the queue, all such kind of questions can be answered. So, as I said, during time t 0 to t 1, you can say it is 0 or t 0 you can call. To t 1, signal is green and the traffic is going through the intersection with traffic state A. upstream downstream of the signal or stop line, the flow condition is same. So, no question of any shock wave. Now, at time t1 signal becomes red, this is the point when the signal becomes red, and therefore, two new flow conditions are formed. Which are those two flow conditions? One is at the downstream of the signal and one is at the upstream of the signal. Now, the flow condition is D is formed immediate downstream of the stop line, there is no vehicle there. If you go further ahead, then the traffic state is A. So, a new traffic state D has been formed with 0 density and 0 flow. No vehicle is passing through the intersection during this red time. And another flow condition is getting created, which is B, formed immediately upstream of the stop line, and here again the flow is 0, but density is the jam density, because vehicles are coming and joining the queue, no movement is happening. So, the density is the jam density and the flow is 0. And altogether this phenomena that the traffic is turning into red, traffic light is turning into red from green, it results in formation of one frontal stationary shock wave. What is the frontal stationary between D and B? And one backward forming shock wave between traffic state B and A, backward forming because it is moving towards upstream as more and more vehicles are joining the queue, and other one forward recovery shock wave WAD, forward recovery shock wave between traffic state A and traffic state D. So, that is the thing. So, now we know how to calculate the speed of this shock wave. So, let us try to calculate the speed of these 3 shock waves. Frontal stationary obviously will be 0, okay. And you can check that WdB equal to Qd minus Qb by Kd minus Kb, right. So, here the Qd is also 0, Qb is also 0, Kd is 0, but Kb is not 0. So, altogether you get 0. Similarly, you can calculate what will be then the shock wave of speed of the shock wave created by traffic state A and D. It is Qa minus Qd, sorry this D is not written properly here, and divided by Ka minus Kd. So, Qa minus Qd is what? 0, flow in the traffic state D is 0 and density in the traffic state D is also 0. So, it is actually Qa by K, which is nothing but Ua, okay? Speed of vehicles travelling in traffic state A. And what will be the omega AB? The speed of shock wave AB, right, which is the backward forming shock wave. It is Qa minus Qb divided by Ka minus Kb, but Qb equal to 0, all other are non-zero. So, it is Qa divided by Ka minus Kj. So, you can calculate if we know the speed flow density of different traffic state, we can easily calculate then what will be the speed. Now, at the end of red phase at time t2, when signal indication changes to green, flow rate changes from 0 to saturation flow rate and a new flow condition C is created, and there again one shock wave is created, which is forward forming shock wave between D and C traffic states, and a backward recovery shock wave between traffic state B and traffic state C. It is recovery because the shock wave created or the Q length what has been created due to the traffic state B and the shock wave A between A and B traffic states, that will get dissipated by this recovery shock wave, which will be created now due to the traffic states B and C. So, again we can calculate what will be the speed of the shock wave created by traffic state D and C, that is WdC equal to Qd minus Qc divided by Kd minus Kc. Now, Qd is 0, Kd is 0. So, it is Qc by Kc, it is nothing but Uc, speed of the traffic state C. Similarly, you can calculate what will be the omega Bc, that is the speed of the shock wave created due to traffic state B and traffic state C, and you will get it is equal to minus Qc divided by Kj minus Kc, and it is minus means moving backward. So, it is backward shock wave. Now, Q will be completely dissipate at the intersection of backward forming and forward recovery shock wave, let us call it at time t3, where these two shock waves will meet. Both are backward, one is forming between A and B, another is recovery shock wave between B and C. They will meet and the traffic state B will vanish. Let us consider that they will meet at time t3. Now, at T3 both backward forming and backward recovery shock waves will meet and a new forward moving shock wave will be formed between traffic state A and traffic state C, because when B vanishes, in between layer is gone. So, A and C directly are meeting, right. So, a new shock wave will be created, which is forward moving shock wave WSC. When forward moving shock wave crosses the stop line at T4, you can see that at time T4 during this green, the forward moving shock wave is crossing the stop line. Then the flow changes from, if I am observing how the flow is happening from the stop line, we will observe then the flow beyond T4 time is changing to a flow rate which was original, like the traffic state A, and this will continue till time T5, where the green time is over and again the signal becomes red. So, what will be then the length of the queue at the end of red signal? What will be the length of the queue at the end of red signal? It will be the speed of the shock wave AB multiplied by the time. At speed, how much will be then the length multiplied by the time? The time is here what? It is the red time. So, red time multiplied by the speed of the shock wave AB. Now, the maximum length Q length is T, that is the maximum Q length, can be determined using this diagram as I have shown here. Omega Bc equal to say tan gamma equal to this St divided by Rs, that is the tan gamma, that is the speed of the shock wave which will be created due to traffic state B and C. Similarly, let us consider WAB, omega AB, that is equal to tan psi equal to what will be that? This will be this St divided by this whole base, that means Rs plus this red portion, that is nothing but the red time. So, from these two equations we can move forward, then St equal to, you can calculate like this, tan psi into R plus St divided by tan gamma using this Rs from this equation. So, like that St you can eventually calculate and you will see it is getting a form like this. So, again this omega will be capital like omega Bc, it has come all in the same line. So, you can calculate then the St values and also you can calculate the additional time Rs, that means once the signal becomes green, then how much time after that it will take to reach to the maximum Q after the end of red signal. So, that R s also can be calculated using this equation and knowing all the other values, right. So, you can calculate this R s also, simple calculation you can follow. I am not telling each and every steps, you can easily follow it. So, what we are trying to see that from this diagram we can actually calculate the ST and RS. So, how much time, what will be the maximum Q length and how much time it will take once the signal becomes green to clear that Q. This is another example which is referring to the temporary speed reduction at a section of highway. So, suppose the traffic are moving like this and suppose a truck enters at a 2-lane highway and traveling at a speed much lower than the other vehicles driving behind it. The truck is entering here with a lower speed. Now, if traffic condition prohibits other vehicles to pass the truck, then the shock wave will be formed. If vehicles are not able to, they will be forced to travel with the speed, same speed of the slow moving vehicle, following that slow moving vehicle. Now, prior to entering the truck, suppose the flow condition was represented by flow state A. Vehicles are moving like flow state A. Here you can say A, here also it is A, because till the time truck has not entered. Truck has entered at this point, at this location and at this time. Now, once the truck enters at time t1 and travels at a reduced speed ub, causing the flow state behind the truck to go to B. So, now again a new traffic state will be created because of the queued vehicles. Queued is not completely stopping, that vehicles are moving with the speed of the truck, but it is a different flow condition now or flow state, that will be B, and also that will create a new flow state D in front of the truck, because immediately in front of the truck traffic state is not A traffic state has gone further ahead. So, in between a new traffic state will be created again with 0 flow, 0 density, that is traffic state D. So, now this itself, this phenomena itself up to this will create 3 shock waves. One is a forward recovery shock wave WAD between traffic omega AD between traffic state A and traffic state D, and 1 or 2 forward forming shock waves. One is between D and B with speed of omega dB, and another between traffic state A and B with a speed of omega AB. Now, suppose at time t2, this is the time t2, the truck leaves the highway and then the flow will be increased to the capacity of the highway and a new flow condition C will be created. Now, as the truck leaves, when the truck entered, 3 shock waves were created. Now, the truck left the road, gone back here, it entered, left the main road, gone back to the side road or minor road. Again this will create 2 shock waves. One is what? A forward forming shock wave between traffic state D and C with a speed omega dc, and a backward recovery shock wave between traffic state B and traffic state C with a speed of omega bc. Now, at time t3, these 2 shock waves, shock wave between A and B and the shock wave between B and C, they will meet, which are travelling with corresponding speed omega AB and omega BC, they will collide, and then the whole traffic state B will vanish at time t3. But then a new shock wave will be created. What will be that shock wave? that shock wave will be created between traffic state A and traffic state C, and that will be a forward forming shock wave with a speed omega AC. Now, track not only affects the traffic stream when it is present on the roadway, but also sometime thereafter. The track left at this point T2, but immediately after T2 the traffic does not come back to its original state, no way, the impact still remains. Now, imagine a driver passes the point where the truck has entered at a time when the truck exited the highway. The traffic state will be not the usual A as it was. Truck is not there, truck has just exited, but then still the driver has to slow down after some time and travel at a reduced speed without knowing even what has happened. He does not know that the truck entered and left, and because he is experiencing still the impact after the truck has exited. The impact is still there in the traffic stream. Now, there could be several variations depending on different traffic state, how is the traffic state A, how is the traffic state B, and so on. So, let us consider some of those. Variation in the flow state A, all others remain same. Now, if the flow state A is assumed to be near the flow state D, free flow condition. Suppose the initial traffic state itself A is very similar to D, then what will happen? Shock wave with speed omega AB would have approached the speed of track UB, right, because that is what you expect. Flow state B and C would have been reduced, the area whatever you are getting now and the overall the traffic state, the presence of this traffic state would have reduced to some extent, and eventually track would have little influence on traffic operation, because traffic state A is equivalent to D, no vehicle. So, what is the impact? A truck enters with a lower speed and leaves it fine. There is not much overall impact on the traffic operation, because traffic state itself is almost a free flow state, very little vehicle or no vehicle. Now, if the flow state A would have been closer to traffic state C operating at capacity, and then this truck entered, slow moving trucks, then the shock wave with speed omega AB would become backward moving shock wave. This line AB would not have been forward moving, it could have been probably like this, depending on, because the impact would be severe. So, the presence of traffic state B will be even further dominant. Earlier case, here it got reduced, but here it will not get reduced, it will be even more prominent. So, we said that flow state B would have been greatly increased, impact would have been much higher. Now, let us consider the variations in flow state B, assuming that all other remain same, just trying to develop some insights, sensitivity in a sense. If truck enters highway between free flow speed and UA, speed of this traffic state A. So, truck enters at a speed which is either equal to the speed of the traffic stream which is moving UA or higher, maximum limit could be the free flow speed. Then what will happen? Then the truck will not delay any other vehicles. Traffic state A is travelling with say 50 km per hour, that is what is the speed of vehicles in traffic state A, and truck enters at 50 km per hour, no impact on the traffic stream. Even try to enter with a higher speed, it will not be able to travel with that higher speed, it has to come down, but then the overall impact on the traffic stream is nothing, no impact practically. Now, if the truck enters the highway between speed u a and u c, lower than this a and u c capacity discharge, capacity flow, then what would have happened? If the truck enters the highway between u a and u c, then the shock wave with speed omega d b and shock wave between a and b with omega a b would have been fast moving. Okay. Now, shock wave omega b c would have been a slow moving shock wave. The speed shock wave actually between traffic state B and C, that speed of that shock wave would have been lower. If the truck enters the highway at a speed close to 0, almost like a 0 speed it is entering, then the traffic state B again would have been significantly increased. Not only traffic state B, traffic state C also would have been increased very significantly. Both would have got impacted heavily. You could have got a larger area of this traffic state A, I mean more dominance, more impact. So, if the truck enters the highway at a speed close to 0, then shock wave omega a b would have been rather faster moving backward shock wave, and flow state B and C would have been significantly increased. So, with this what we discussed today is about the quantitative analysis, speed of shock waves, how we can calculate, knowing the lower higher two traffic states, whether the density, how the densities compare, how the flow compares, right. In the flow density curve itself, comparing two traffic state, we can say whether the shock wave which is going to be created in between two traffic state is going to be forward moving or stationary or backward moving. Then we took an example of how the shock waves are going to get created, different traffic states are going to be created and dissipated eventually due to the operation of a signalized intersection. And also another example we took where the speed is temporarily getting reduced on a section of highway, because the slow moving vehicle is entering and then travelling some time and then leaving the highway again. And then again, most interestingly, we have seen that how things would have been different depending on various possibilities of traffic state A and also various possibilities of actually variation in the traffic flow state B, but primarily depending on at what speed the truck is entering, how that would have impacted the traffic flow state B and also traffic flow state C, right. So, with this let us close this lecture. Thank you so much.